And he will tell us about
once reinforced
random walk. Thank you very much.
Right. Okay. Happy to be here again. Okay, so let's and okay, maybe I'll start by defining the model so that people will know what I'm talking about. So it's a model of self-interacting random walk or random walk with memory. And the definition is very easy. So, okay, so let me first of all name it once reinforced random walk. And the model is very simple. You have, it's a model of a walker that has a slight preference to edges that it's already visited. So let me draw some picture in a picture in 2D. So the walker starts in the beginning. In the beginning, it hasn't traversed any edges at all. So there are no preferences. So it just chooses randomly between the two edges. There are four edges, and say it goes to the left, for example. But now, but that's just the first step. Now we are looking at the second step. In the second step, he already traversed this edge. So he has a preference, and the preference is quantified by a parameter called A. So A is some positive number. And what the walker does on the second step is to put 1 on all the edges it hasn't traversed yet, 1 plus A on the edges that it has traversed, and then normalize these numbers to probabilities, just divide by their sum, and walk according to this probability. So here it would have like probability 1 over 4 plus A for each of these three, and 1 plus A over 4 plus A to go back to where it started. If A is very large, then he will be quite prone to do that. If A is small, then this will only be a small preference. And so on. So, for example, suppose it went here and then went down and then went up, and now it's here. Then in the fourth step or fifth step or whatever you get, 1, 2, 3, 4, fifth, then it already has two edges that it already traversed. So the way the probabilities are similar. So 1 plus 4, 1 divided by 4 plus 2, and 1 plus A divided by 4 plus 2A for the two types of edge. So the weight, the formula for the weight is simply 1 plus A times the indicator that the edge was visited in the past. And historically, the model was developed together with a related model called linearly reinforced random walk. So this is the once. This is called linearly reinforced random walk, and which is the same, except the weight is 8 times the number of visits of that edge. So the weight of each edge is the number of visits to that edge. So in the linear model, every time you pass the edge, you add an A. So it's 1 plus A after first, 1 plus 2A, 1 plus 3, and so on. In the once, it's only either 1 or 1 plus A. So these are the two. So the talk is about once reinforced, but historically, you can talk about one without talking about the other. It makes sense, but the linearly certainly was looked into. Once there are so few results on ones that that I can't think of a direct result. But the linearly certainly was, I can mention the directed result. Okay, questions about the definition of the model? Also in the chat? No, nothing in the chat. Okay, so so now that we have our two actors, let's do the historical presentation. So it starts in 1980 with work of Diaconis and Friedman on partial exchangeability, something related to De Finetti's theorem. Whoever knows what is De Finetti's theorem, that's good. If you don't, that's even better. Which led to the definition of linearly reinforced. So the linear was the first to be defined. And they asked the following question: what happens in Z2? So, and this question became quite famous with time. So when you do the linearly reinforced on Z2, so you would want to say, well, even without reinforcement, it's recurrent. And reinforcement makes you like better places where you've already been. So surely it should be recurrent also in this case. And the problem was not so easy. So, but anyway, this was somehow the work on the Finetty theorem led naturally to this definition. The model is quite special, and then they asked this question. And the next point was in 1988. Now it's a theorem, yes. Who in 1988, Pimentel he worked on trees. And he showed a phase transition. So what do I mean by phase transition? What is the parameter even? The parameter is A. Infinite regular tree, yes. So working on an infinite regular tree showed that there is a completely different behavior depending on the value of A, which maybe a priori you wouldn't think makes much of a difference asymptotically. But that's not the case. What he showed is that if A is sufficiently small, then in fact the random walk looks like random walk on a tree. It's transient, it goes to infinity ballistically and never comes back. While if A is sufficiently large, what you have, maybe I will keep this here and just write it here. If A large, then what you have is an even more stronger thing than recurrence. You get positive recurrence. So what is positive recurrence? Positive recurrence means not just that you return to where you started from, but that the expected time to do that is constant. Doesn't grow to infinity with time. Or, well, it's finite. Well, okay. Right, okay, for a random walk that would mean just that it's finite, but in this case, it means that basically the walker spends a constant proportion of the time in the starting vertex. Okay, so is the statement clear? Is it clear what is positive recurrence and what is the result of Pimentel? And this, no. There is a strict phase transition. Trees can be completely analyzed because there is much less. What happens here that in a tree, you are here. Suppose you decided to go here and add an A. There are only two possibilities. Either you come back from where you left, and then you are here, and the weight is 1 plus 2A, or you never come back, and then who cares? So all the vertices are independent. And this only works in a tree. This independence of vertices is what makes the tree analyzable. all the vertices are independent. Each vertex is a Poya-Ern, for people who know what it is. If you don't, that's fine. Because, again, the topic is once and not linearly. And you analyze it via that, and the Poya-Ern are completely analyzable, so that's how the proof goes. Probably. Should be. I see no issue here. Wouldn't be very nice because there are Bessel functions involved, but there should be. Not Bessel, this B function, this partial, whatever, some special functions. Okay. And after that, there was a long hiatus in work on the Diaconis-Friedman conjecture, and once reinforced was born during that time, originally as a toy model for linearly reinforced, because the people were just well, it was already 20 years old and no progress. And then in 2001, Duret, Kesten, and Limit they analyzed once reinforced random walk on a tree and showed that there is no phase transition. So for once on a tree, regardless of, you actually get the behavior which maybe you would have conjectured to start with. The value of A doesn't matter. Small or large, you're always transient, ballistic. You don't really feel the value of A, say, asymptotically. Okay, so is the statement of the result clear? Okay, so this result somehow demoted once reinforced random walk from a toy model to a bad toy model. But, life is full of surprises. Then in several rather important papers, 2008 to 2009, Merkel and Rolles did the linear case on Z2. And they proved eventually. No, okay, they didn't quite formally prove this conjecture of Diaconis-Friedman, but they essentially proved it. They proved something quite close to recurrence. And anyway, they showed some very, I'm not going to state the result exactly, but some pretty strong pretty strong comparison between the linear case and just the unreinforced, just the usual random walk. So showed some kind of domination, which was allowed you to get a lot of information about about the behavior, but not recurrence, but a lot of information. So I consider this a really an important breakthrough. And then maybe 2009, maybe 2010, I'm not completely sure, came Sidorovicius conjecture. And he asked about once, and he made the conjecture that if you look at once reinforced random walk on ZD, then you do have a phase transition. So, but this is a conjecture, right? So this is a conjecture. So he conjectured, Vladas Sidorovicius conjectured, that you have a phase transition in A, not exactly like for linearly reinforced, but still a noticeable phase transition. So it's not positive so again, the conjecture is that if A is sufficiently small, the walk is transient and looks like and looks like random walk. And if A is sufficiently large, it's not positively recurrent, but it is recurrent. And the conjecture is that it actually looks like a man jumping inside an inflating balloon. So if you look at the set of visited edges, so let me denote by W the process itself, and then W 0t, I will use this notation throughout for just the set of visited vertices or edges or vertices or whatever I feel like at the time. Okay? And he conjectured that for A sufficiently large, this set looks like, in some sense, t to power 1 over d plus 1 times k, where k is some convex set. So again, the set of visited edges, vertices, looks like a slowly inflating convex set. You will notice that this means that because the volume is t to the d over d plus 1, this means that the volume is much smaller than the time. So in fact, it visits every edge typically many times, in fact, this amount of time. And in particular, it's recurrent, but not positively recurrent. Somehow, the conjecture is that at time t, you have visited 0 approximately this amount of time. It's a, well, I mean, it looks, there is some case such that asymptotically, you look more and more similar to K. No, it should depend certainly on the dimension and probably also on the graph normally, but yeah, but this is a conjecture. You can conjecture whatever you like. Yes, it depends on it. Depends on it. Yeah, it should depend on it. It should depend on it. Yes, certainly. It should depend on it. That's what any reasonable person would conjecture. Okay. Now, around 2014 and 2015, too many people to mention, or at least to write down, did a very thorough work on linearly reinforced on lattices. So I'm not going to write down all the names, but main characters are Pierre Tarès, Christophe Sabot, Margherita Di Sertori, based on all the work of Margherita Di Sertori with Tom Spencer and Martin Zierenbauer. Also, there's a paper of Omer Angel, Nick Crawford, and myself. Another paper of Pierre and Christophe with Shaolin Zheng. So, too many people to write down. But the but the result is are very detailed, and you have a phase transition in all d bigger than 3 on a lattice. So again, a sufficiently large, you have a sufficiently small, you have random walk behavior. A sufficiently large, you have positive recurrence. Plus this Diaconis-Friedman conjecture. They also proved that as part of this big, there was a huge, that progress came from understanding relations to the Anderson model. So maybe given the topic of this special semester, maybe I should have talked about that, but I don't have any new results about linearly reinforced, only about once. And anyway, I gave that talk already here 2 years ago. So, so, so I'm not going to go into what's the relation to the Anderson model and so on, but just to say that it was used to to learn something small about Anderson, but mostly to analyze this model quite thoroughly. And this is still an ongoing research. I wrote 2014, 2015, but this is still going on. People have understood the phase transition, like the two phases sufficiently well that now people are focusing on understanding what happens at the transition and so on. So this is a really well understood model, and once reinforced, stayed open. And let me just mention one. Yes, yes. So, and there is not so many. I'm not mentioning any one-dimensional results. There have been one-dimensional results. I'm skipping them. I think they are not very enlightening. Um, no, here I would need my notes to spell. Kolevbekian. There's no double C. Maybe there is a double C. Okay. Should be a double C, I guess. So they did once reinforced, but still on something infinitely dimensional. So say on a, okay, for people who know what is a non-amenable group, that's fine. People who don't know, they are not missing much for this talk. And the new result, the result that I want to talk about, is once reinforced random walk and A large. Sorry, A small. Is on ZD, D bigger than 6, and A small. So again, so this is our result, the result I want to talk to you about. We look at once reinforced random walk on ZD. Unfortunately, we cannot make it all the way to 3. We have to stop at 6, for reason that hopefully I will be able to explain in the first hour, but if not, then in the second hour. And A sufficiently small. And in this case, we prove this half of Sidorovitch's conjecture that in fact you have the transient phase, the phase that the random walk just goes to, just looks like random walk. That the reinforcement doesn't change the picture asymptotically. Okay, so questions about this? It depends on the dimension, certainly. And we didn't bother to try to well, there is an A naught that depends on the dimension, such that if A is smaller than A naught, we don't show, first of all, you can't even talk about, when you analyze phase transition, there are like the three stages. First of all, you show that there are two phases. After that, you show that there is a unique transition. Okay, because a priori, if you only analyze A small and A large, then it might flip several times, or it might be intermediate transitions. And then the third thing is to understand what's happening at that critical value. We are in the middle of the first step because we only showed one of the phases. So it's a bit premature to talk about how the phase transition looks like. Yeah, here, for example, for the linear, they already know that the phase transition is unique. This is Sabot, Ares, and Zeng. And now they are trying to understand how it looks at and near this transition. But for once, right now we have only one phase, and the somehow, in a sense, maybe more surprising side of Sidorovitch's conjecture is still completely open. Okay, any other questions? Maybe in the chat. Sidorovicius. So that's an R and that's a V. I apologize that my R's and my V's are essentially homomorphic. Vlada Sidorovicius. So he could, well, first of all, you need, the most interesting thing is, no, okay, dimension, that's for me less interesting. It's also interesting, but to show the second phase, to show that there is a recurrent phase, we don't know that. Okay? Any other questions? Okay. Okay, so that was the exposition. It wasn't long. The rest of the hour and a half would be a proof. Um, uh, um, right, I promised to say something about the directed case. The directed case has the same property that you have on a tree, that all vertices are independent. Because if you don't care where you come back, in the directed case, you don't care where you come back. So all vertices are independent. That actually doesn't make the model trivial. That you put weights differently on directed edges. And then the behavior at every vertex is independent. That doesn't make the model trivial, but the linear reward is analyzed using that, and some things are not everything, because even independent polyiron, if you put them everywhere and analyze them, it's not so easy. But a lot of it is known via this approach. Okay, any further last chance for questions before I start the proof? Okay. Okay, so the proof certainly doesn't fit, not in an hour, not in 2 hours. Uh, but I'll tell you a few things that I like from the proof. Sure. Right, Z2. So there is a super interesting question which is open in 2D for linear, even for in the linear case. Which basically ask whether it's always recurrent, but there might be a phase transition relating to positive recurrence. So there might be a critical A such that for below that you are positively current, while above that you are recurrent but not positively. This is completely open, judging by its relation to other problems in probability. It's probably exceptionally big because it's related to Polyakov conjecture. I don't know if people know what it is. Nobody has a clue how to do that. But and this is for me the most interesting question that remains in 2D. Again, I did some simulations even, and it wasn't completely clear whether there is a phase transition. Again, the same vague connection to Polyakov's conjectures say that if there is no phase transition, then there is no way to see that in a computer. Because it won't help you too much, but okay, I don't mind telling you what it is. So Polyakov conjecture is about, are people familiar with Ising model? The Ising model? Okay, so Polyakov conjecture is about a cousin of the Ising model. Okay, I'm just going to say that. So you take some box in ZD, and your configuration is a function from the box, but not to plus minus one like it would be in Ising, but to the two-dimensional sphere. And but other than that, it's similar to Ising in the sense that you define the Hamiltonian as a sum on all neighbors of omega, let's say distance of omega I, omega j squared. Is it important squared? Maybe it's important, but I don't think it's important. And then the question is whether you have a phase transition or not. The probability of any configuration, okay, not the probability, but the density for every configuration is proportional to exponent of minus inverse temperature h, and then the phase transition would be in beta. So that's Polyakov's conjecture. I don't want to state it in more details than that. The people who are familiar with Ising can finish the details. People who are not so worse off. That there isn't. There isn't. That there is no. So that there is no Kosterlitz-Tarless phase transition. Okay, it's too long to state. You know that there is no phase transition like in the Ising. This is a result of Mermin and Wagner from the 60s, that such models don't have a phase transition, a classical phase transition in two dimensions, but there must be a phase transition between polynomial and exponential decay of correlations. And Polyakov's conjecture is that it's actually converged exponentially. The correlation converged exponentially for all values of beta. Okay, no, we have 2 hours, so.
Evaluation that is so negative
Right. But S1 is completely analyzed in a sequence of in a very difficult paper of Froelich and Spencer from 81. And the other spaces, well, physicists somehow conjecture in some sense that if it's a symmetric space, this conjecture is so easy to find counterexamples to. Okay, there is a conjecture in physics, but it's too vague to state in a mathematical talk. But somehow S2 should be like some kind of, if it's really true that what plays a role is whether the symmetry group is abelian or not, then S2 should be the most interesting case to study. Let me put it this way. But this is that's even more remote from our understanding. Okay, so this is in the linear case. In the once reinforced, as I said, I did simulations. I don't even know what to conjecture. The simulations were rather vague, in the sense that it looks like a phase transition, but then you do longer simulations, and then it looks like maybe the phase transition shifted a bit, so then maybe it would shift all the way to the end, maybe not. So I don't know. Okay. Okay? Great. Okay, so let me start by the most simplest explanation of why high dimensions. Okay, and this explanation will at least explain why we need 5. It won't explain 6, that would be much trickier, but it will explain why we need 5. So what happens in 5 dimensions? How is random walk in 5 dimensions different from random walk in lower dimension? And this is quite easy to explain. And what happens is that if D is at least 5, then two random walks don't intersect with positive probability. So what do I mean? Well, I mean the traces. So let me just prove that. Well, okay, I'm not actually going to prove that, but at least indicate the calculation. So what is this probability? This is the probability that there exists two times, T1 and T2, such that R1 of T1 equal to R2 of T2. Okay? But the probability that something exists is certainly smaller than the expected number of times that it happened. So this is certainly smaller than the sum over all T1 and T2 of the okay, let me write it like this. But this is just the probability of one walk of length T1 plus T2 returning to 0 by translation invariance, which we know from standard facts about random walk in ZT is approximately up to constant T1 plus T2 to power minus D half. And now you immediately see the role of 5 dimensions, because you have here, we are not requiring them to be at the same point at the same time. That would be here, for that 3 dimensions would be critical, but we are requiring them to be at the same point in different times. So you have a double summation, which adds a 2 here. And for this to be negative, you need the D to be at least 5. Okay, so I didn't I, di- I didn't explain why finiteness gives you that the probability is positive, but this is some kind of standard manipulations. Uh, so this is why 5 dimensions are necessary for the kind of techniques that are involved. And a corollary of that is that a single random walk doesn't intersect its path with positive probability. Yeah, right, my constants are always positive, right? I think I assumed it was clear, but so and this is exactly the same, because this is just a random walk. Okay, after time reversal, the only thing this comes from this by just time reversing the first part, and okay, and chopping it. Okay, so what happens is that in 5 dimensions, at any time has a positive probability to be a cut time. But think of our models once or linearly, it doesn't matter. If you have a cut time, then you forget about the past, then the interaction no longer matters. So, so if you could somehow, of course, this is a circular argument, right? You assume that it looks like random walk. You get, then therefore the interaction doesn't matter, and you conclude that it's a random walk. So that's not a proof of anything. It's a circular argument, and of course, certainly wouldn't explain why there is a phase transition. The circular argument cannot be justified always. It needs to be justified under some conditions. But at least it gives you an indication why 5-dimensional special. In fact, the paper of Elboim and Sly, which we are basing on, actually takes a completely different interaction and shows that in 5 dimensions or more, it looks like random walk. So this is the kind of a generic this paper of Elboim Sly is a relatively generic result that's saying that could probably be somehow axiomatized, that if you have an interaction that satisfies this and this and this, then in dimension sufficiently large, and it looks like random walk. And also our paper, our proof, where we will explain that a little bit, is could be axiomatized if probabilists were the kind of people who axiomatize things. Yes. This is just a proof for random. Yes. No. But I'm saying that no, this doesn't work for once because, and of course, it couldn't work for once because we are assuming that there is a phase transition. So yes, no, but the proof does actually give you a hint how to start. Okay, so how do you make a circular argument? How do you rigorize a circular argument? You make the circle into a spiral. So you make you okay. So I'm erasing. Uh, wait, I already have to make a break, right? Okay, no, but it's not such a bad point to make a break. But let me still write something on the blackboard and then make a break. So, what is the? So I will just write the proof strategy in vague terms. So what is the vague term? So okay, the first thing is not vague. We are going to do an induction over time. Okay, t, but t is time. And what we are going to show is that, okay, now it's going to be vague. Now comes the vague part, that if A is sufficiently small, then once reinforced random walk looks like random walk up to time t. And this is going to be proved by induction over t. So this is the basic strategy. The strategy in its own was known a long time ago. In some sense, since the 80s at least. But it's not so easy to make this work. You need to find the best way, a way to make that into a rigorous statement that will allow an induction to work. And the smallness of A comes in the induction basis. Okay, so I think that's after writing this, that's a good place for a break. So in next hour, I will probably state the induction assumptions almost rigorously. And maybe show you one lemma that I like from the book.